Chapter 10, problem 49. A uniform solid disk of radius r and mass m is free to rotate on a frictionless pivot through a point on its rim, as you can see in this figure below. So this is the disk, and this is the one of the rim is the pivot. If the disk is released from rest in the position shown by the blue circle, which is over there, what is the speed of its center of mass when the disk reaches the position indicated by the dashed circle, as you can see in here, right? That's the question one. Question two, what is the speed of the lowest point of the disk in the dashed position, which means they are talking about the point in here. This is the lowest point in this dashed position. And the last question, what if, repeat the part A using a uniform hoop. So instead of having a uniform solid disk, you'll have a uniform hoop. Then in this case, what would be the speed of the center of mass when the disk reaches the position indicated by the dashed circle? Of course, we expect in principle that what changes between the hoop and the solid disk is the moment of inertia. This is all. Let's solve this problem. So we have, this is the figure, and in the first question, we are requested to determine the speed of the center of mass of the disk when it reaches the position indicated by the dashed circle. So how much is V, center of mass, in this new position in here? اللي هي dashed circle, يعني vertical position خلينا نسميها. So let's see first what happens when this disk rotates. The center of mass of a disk is defined by the central point, by the geometric center اللي له. So عمليا هو هذا البوينت اللي موجود على النص على الcenter. Let me just draw it in a proper way. So this is the center in principle. And when this disk rotates about the pivot, has point مثل أي point تاني حيبرم على circle, right? And this circle اللي حيبرم عليه هو عملياً a circle of radius r لأنه هو على بعد radius r من axis of rotation. So this is the point center of mass when it is in the initial position اللي هي let's say horizontally كانت center of mass. وهيدا هي البوزيشن final position when it reaches disk reaches this position. هيدا هو بيكون هون نقطة center of mass. So السؤال هو قد ايه ال V of the center of mass at this position downstairs. قد ايه ال V هون. So this question is in principle very easy to solve if we choose the correct method. بالمبدأ نحن فينا نشتغل هذا السؤال بأكثر من طريقة. However, إذا ما نختار طريقة Newton's second law, for example, and we're going to apply all the forces acting on this system and to apply Newton's second law for rotation, so the torques لكل force عم تعمل action على هالdisk, and then we are going to see what is alpha and then what is V. It's going to be not quite easy to solve it. However, there is a much easier way to solve this problem where we can use an alternative approach to the Newton's second law اللي هي the energy approach. Actually, this system اللي هو our disk and the pivot together with the earth, it makes an isolated system where you don't have any non-conservative forces acting. The only force would be the gravitational force exerted by the earth on this disk and the normal force exerted by the pivot on the disk, and both are conservative forces. So we have an isolated system, its mechanical energy is conserved, and we can apply conservation of mechanical energy between this initial position when the disk was horizontally hold on, and then when we, after being released, it reaches the dashed position. So between initial and the final state, we can apply conservation of mechanical energy. And so let's write this down. So we have conservation of mechanical energy of the disk between initial state and final state as given by the initial position, and so the full line position and the dashed line position, بيطلع معنا انه mechanical energy is the same. So بالinitial state we had so k final plus u k initial sorry plus u initial is k final plus u final. Initially in the given it says that the disk was released from rest, which means that k initial is equal to 0. K final is of course different than 0. It has an expression for the rotational kinetic energy لأنه هون الأوبجكت عم يعمل rotation. And then we still have the gravitational potential energy. We need to determine one of the two positions to be reference for our gravitational potential energy. So let's take the final, let's take this line where the center of mass is to be our reference, right, for gravitational potential energy. If we choose this to be our reference, then we can say that U final is equal to 0 لأنه بالفاينل position كانت على 0. Okay, and so this allows us to write down. Initially, the gravitational potential energy was given by m multiplied by g multiplied by the position of the center of mass, and the position of the center of mass was given by r. Right? So m times g times r is equal to half. We have kinetic energy of rotation, so it's half I omega squared, where I is the moment of inertia of this solid uniform disk, which is equal to half mr squared. And so let's write down then, we end up with m squared, omega squared is equal to 2 multiplied by m times g times r divided by I. And since I is half 2mg times r divided by هلا هون اوكي رح تخليها I with given that, or let me just move this لأنه ما حطيتها بقيمتها. And let's just precise how much is I. So I is the moment of inertia about the rotation axis, and we know that given I center of mass is equal to half mr squared, right? So then the question is, how much is I؟ هل فينا نحط الهاف mr squared بقيمتها مباشرة ونكمل؟ الجواب هو لا. ليش؟ لأنه هو عاطينا بالجيفن اللي هو بالكتاب يعني إنه ال I center of mass is equal to half mr squared. But this disk is not rotating about its center of mass. It's rotating about this point, which is parallel to the axis passing through its center of mass. هي عم تبرم حوالي هيدي النقطة, axis passing through this point اللي هو البيفوت, وهالنقطة بعيدة عن السنتر اوف ماس distance r, والاكسس مارق فيها parallel على الاكسس اللي مارق through the center of mass. So we have to apply the parallel axis theorem. And according to the parallel axis theorem, we know that the moment of inertia about the pivot that we are looking for, it's given by I center of mass plus mass of the disk multiplied by the distance d squared between the two axes. The I center of mass is given by half mr squared plus mass of the disk multiplied by distance ما بين اثنين axes هي r مثل ما حكينا, هي هيدا distance r. And so all what we need to know is all what we need to then replace is d by r. بصير في عنا d equals to r, and so we end up with 3 over 2 mr squared for the moment of inertia about the axis of rotation. And so here we end up with omega squared equals 2 times mg r divided by 3 over 2 mr squared. Okay, هلا هون شو بصير؟ أول شيء الm it cancels out مع الm in the numerator and the denominator. هيدي ال 2 هون بتطلع لفوق, بتصير في عنا بدل ال 2 في عنا 4 لأنه بتنضرب بال 2 times g. ال r up there would cancel out with 1 of the r squared تحت بالdenominator, بيطلع عنا 4g divided by 3r. هيدي هي الإكسبريشن omega squared, and so we can deduce from here that omega is equal to square root of 4g divided by 3r. But this is still not yet the answer. لأنه إحنا مش عم ندور على angular speed. نحن the question was how much is the speed of its center of mass when the disk reaches the position indicated by the dashed circle. So we are looking for v center of mass. But as you know from the relations between the angular variables and the linear variables, that the linear speed, it's related to the angular speed through the radius r, where r is again the radius of the circle along which the center of mass is moving. طيب نحن مثل ما بنعرف center of mass هو ماشي على circle of radius r with respect to the axis of rotation، لانه السيركل هو لانه السنتر اوف ماس مساوي هو بنصه للديسك. فلهالسبب هون الار اللي عم نحكي عنها let's call it r center of mass هي الار multiplied by square root of 4g divided by 3 times r. هلا اذا بندخل الار لجوا بصير في عندنا سكويرد، فبيطلع عندنا 4g r squared over 3r. So r and r cancel out and so we end up with 2. الفور كمان فينا نظهرها لبرا بتصير 2 square root of g divided by gr divided by 3. And so this is it. هيدي هي الاكسبريشن لل v center of mass يلي نحن كنا عم ندور عليها. This is it. So as you can see, using this alternative approach اللي هي الapproach of conservation of mechanical energy, things get much easier instead of applying Newton's second law, for example, for this kind of problems. Now, the second question was, I will read it. What is the speed of the lowest point on the disk in the dashed position? طيب هاي هي الداشت position اللي عم نحكي عنها، هيها. Lowest point هي هون. I will call it B, just to say it's the bottom, okay? So the question is, how much is VB, right? And this sounds easy also as well, because we are going to apply exactly the same thing. But part B here, how much is VB? طيب this point is part of the disk, right? ولما الديسك يبرم هي عم تبرم معه كمان. بس قد ايه السبيد له بهالنقطة هيدي؟ بهالنقطة ال V لل B هو عبارة عن R B multiplied by omega, because B it rotates with the disk at the same angular speed اللي هي الأوميجا، بس its linear speed هي لها علاقة بقد ايه بعيدة عن الأكسس of rotation. قد ايه بعيدة عن الأكسس of rotation هي عمليا 2R. So we end up with 2R times omega. And so if R omega is equal to 2 multiplied the square root لل GR over 3 فهون بيطلع معنا هي عبارة عن 2 multiplied by 2 times square root لل GR over 3. هيدا الار اوميجا جبتها من السؤال اللي قبل لانه كنا بعدنا جايبينه، فبيطلع معنا هي عباره عن 4 times square root of g r over 3. So this is the speed of the point B. That's number one. And number two, just one comment, is that you can immediately realize here that the speed of the point B is equal to 2 multiplied by V center of mass، لأنه هي عبارة عن شو؟ هي عبارة عن 2 multiplied by R omega، بس ما إنه ال R omega هي نفسها ال V center of mass، ففينا نستنتج مباشرة إنه ال VB هي 2 times ال speed of the center of mass. So this is it for the part B. Now let's move on with the part C. And in part C, we will have a hoop instead of this. So in this case, we will have omega squared is equal to 2 times m times g times r divided by I of the hoop. Right? Because actually it's the same case لأنه إذا كان في عنا hoop الهوب السنتر اوف ماس اللي لاقي هي السنتر تبعولها. سو عمليا لما تبرم من الهوريزونتال بوزيشن للفيرتيكال بوزيشن the difference in the gravitational potential energy هي كمان defined by mg times r. So بيطلع معنا نفس النتيجة. However, I hoop is different in this case because actually we know that for the hoop I center of mass of a hoop, it's given by m multiplied by r squared, right? So if you want to determine I of the hoop with respect to P, let's call it I hoop with respect to P. And here is the point P. So I of the hoop with respect to P, it's given by I center of mass plus m multiplied by d squared according to the parallel axis theorem. And so we end up with mr squared since d is equal to r again in this case لأنه ما بين center of mass وما بين pivot distance هي radius, so plus mr squared, and so we end up with 2 times m times r squared. And so if you replace I hoop by its expression, we'll end up with omega squared equals 2 times mgr over 2 m r squared. And here there are plenty of terms which cancels out between the numerator and the numerator. And so we end up only with omega squared equals g over r. So we end up with omega equals square root of g over r. And since we are looking for the speed of the center of mass, so again here v center of mass is equal to the radius r multiplied by omega, because again for this system اللي هو الهوب, the center of mass is in the center and the radius of the circle along which the center of mass is moving هو نفسه ال R للهوب. And so it's given by so R multiplied by square root of G over R. بندخل ال R لجوا بتصير عنا R squared, and so we end up with square root of G times R. And so in the case we have a hoop instead of a uniform solid disk, we end up with the speed of the center of mass given by square root of G multiplied by R.